This is lecture 3, and it's covering incompressible fluid flow rate measurement system, or equipment and systems. Okay. So today we're going to cover first off what's the purpose of flow rate measurement? Why do we need to do it? We'll look at Venturi meters. Okay, that's one type of measurement system. Sharp-edged orifice meters and pitot-static tubes. Some of you may have heard of the pitot-static tube before. And then we'll look at an alternative configuration of pitot-static tube specifically designed for gases. Okay. Why do we need to measure flow rate? Okay. Well, basically it's for measuring speed and flow. Okay. So we're looking at systems to measure speed and flow. And what are the applications of such system? Well, with a fire engine, obviously there's going to be a pump that's sending water to a hose. And to measure that flow, we can use what's called a Venturi meter, which I've got a picture of here. Okay. And so there's a dial on this thing that will give a gauge of how fast the water is flowing through that hose. Okay. Aircraft speed, airspeed. Okay. If next time you're at the airport and you can see the plane, take a look and see if you can spot one of these things. It's a pitot-static tube, and that's there to measure the speed that the aircraft is moving through the sky. Okay. And obviously you can apply the same principle to a boat, and you get a water speed for watercraft. Okay. So these are applications of flow rate measurement devices, and we're going to look at each of these: a Venturi meter, a sharp-edged orifice meter, and a pitot-static tube, and show you how they work, and we're going to talk about some of the maths behind it. Okay. So the first one is the Venturi meter. Okay. Essentially what we've got is we've got a converging, diverging, nozzle-shaped system. Is everybody okay up there? And so you've got a converging, diverging nozzle. We've got flow coming in like this. The fluid density is a constant. Okay, we're dealing with incompressible flow, so we know that rho is always going to be the same. And essentially, as we know, we've got a pressure here, P1. Okay, and this part of the pipe is known as a convergent part, and that's because the area of the pipe is contracting. Okay, it's getting smaller. And then we have what's called the throat, and that's where our P2 is. Okay, and then to go back up to the original area, we then have a divergent pipe where the cross-section over the pipe expands. And we know from continuity that V dot, the volumetric flow rate, equals A times C. And because of this relationship, we know that as the area reduces, the speed increases, yeah? This is like the example I showed you a few weeks ago with the ping pong ball. The area around the ping pong ball was reducing, so the speed went up. Now, what do we know about Bernoulli? Well, Bernoulli says that the total pressure is constant, okay? And if we ignore the Z term here and we just have the P and the 1/2 rho C squared, well, if C goes up, P must go down, yeah? Because the total pressure is a constant. And so we know that the increase in speed leads to a decrease in pressure. Okay, and so there's going to be a difference between P1 and P2. And that difference means that P1 is greater than P2. So there's going to be a pressure difference of P1 minus P2. Okay. Well, how do we measure this pressure difference? Well, we can use a U-tube manometer, like we did in the first lecture on fluids. And so you've got this U-tube manometer. Let's say that we've got water flowing through the pipe, and we can use perhaps a mercury-based substance for the manometer fluid. Okay, and we can know we've got points A and B here, and because A and B are the same level vertically, okay, we know that their pressures are going to be the same. And so we know that pressure at A equals the pressure at B. Or mathematically, you can write PA equals PB. But what are PA and PB? Well, we can work them out. They're very simple calculations. we know that the pressure at A is going to be the pressure P1, which is the static pressure, okay, plus the amount of fluid above P1. So if we had water there, then we'd have the pressure at P1, okay, here, and then we'd have the amount of water above P1 to the point A, okay, and so that pressure at PA is going to be P1 plus rho g times by the head, and the head in this case is HP plus Y, okay, the total head from the level of A up to the centre line of the pipe is HP plus Y. And so we've got P1 plus HP, P1 plus rho g HP plus Y, okay, is the pressure at A. The pressure at B is the same sort of thing. We've got P2, and then we've got the distance Y of our water, okay, and the distance HP of, say, mercury. And so you have to add them both together. You get P2 plus rho gy plus rho m, which is the manometer density, okay, times G times HP, okay. So we've got these pressures, A and B. Well, as we said, they're equal to each other, so we can equate them together, and you end up with this equation. And then by doing some manipulation, we can solve for P1 minus P2, which is the pressure difference, the pressure drop. Okay, and we end up with this equation. Well, you can notice from this equation that we've got 2 rho gy's, and one minus the other means that they disappear. And so you can cross them out, and you end up with this equation. The pressure difference is rho m, so the manometer density, times by G times HP, minus rho of the water, or whatever fluid you're measuring, times by G times by HP, okay? Now, obviously, we can take the rho's out of that equation, or the GH out of that equation, and you end up with this equation. P1 minus P2, which is our pressure difference, equals the density of the manometer fluid minus the density of the fluid that you're measuring, times by G, times by HP. And this is known as the pressure difference. Okay, so that's fine when the manometer is flowing with a liquid. Okay, so when the fluid is flowing through the pipe as a liquid, we know that rho m and rho, so the manometer density, manometer fluid density, and the fluid that we're measuring density, they're of the same magnitude. So, for example, water is 1,000 kilograms per meter cubed, okay, and mercury is 13,600. So they're of the same sort of order of magnitude, okay. So we need to include them both in the equation, and so we end up with this equation, which you've just seen. Okay, but when you're dealing with a gas, okay, the density of the gas is going to be a lot smaller than the density of the manometer fluid, okay? And so, because the density of the gas is so small, for example, if you were still using mercury and you were measuring air that, say, has a density of 1.2 kilograms per meter cubed, obviously the density of air compared to the density of mercury is massive. So we can actually neglect the density of the fluids that you're measuring. And so you end up with the pressure difference just being our nice hydrostatic equation, rho g h. Okay? So you'll all remember that. And we know that P1 minus P2 is known as the pressure difference. Okay? So if the question is asking, if the question is saying, well, what's the pressure difference around the throat, or between the throat and the pipe, then this is what you're looking for, P1 minus P2. Okay.